What if I told you that everything you've ever known, every star you've ever seen, every galaxy stretching across the cosmic horizon, might represent just one tiny bubble floating in an infinite ocean of realities? That beyond the edge of our observable universe, there could be countless other worlds where different versions of you are living completely different lives, where the laws of physics operate under entirely different rules, where universes are born and die in cycles we can barely comprehend. Welcome back. I'm so grateful you found your way here. And before we dive into tonight's cosmic puzzle, I'd love to know where you're listening from and what time it is in your corner of our vast universe. If you find yourself drawn to these deep questions about reality, consciousness, and our place in the cosmos, I'd be ever so thankful if you gave this video a like and perhaps subscribe to join our community of weary researchers. Now let's get started. The story begins now. The story we're about to unfold isn't science fiction, though it certainly sounds like it. This is cutting-edge theoretical physics, where the boundary between what we can observe and what might actually exist becomes beautifully, mysteriously blurred. We're talking about the multiverse, one of the most extraordinary and controversial ideas in modern science. It's a concept that suggests our entire universe, with its 100 billion galaxies and 13.8 billion year history, might be nothing more than a single frame in an infinite cosmic movie. But here's what makes this story so captivating. Unlike the fantastical parallel worlds of comic books and movies, the multiverse theories we'll explore tonight emerge from rigorous mathematics and careful observation of our cosmos. They arise naturally from our best understanding of quantum mechanics, cosmic inflation, and the fundamental structure of space and time itself. These aren't wild speculations, but logical extensions of physics we can test and verify in laboratories around the world. The journey begins with a simple yet profound realization about the universe we can actually see. When you look up at the night sky, you're not seeing everything that exists. You're seeing only a tiny fraction of reality, limited by the fundamental speed of light and the finite age of our universe. This boundary, called the cosmic horizon, marks the edge of the observable universe. Beyond it lies a mystery that has consumed physicists for decades. Imagine standing on the shore of a vast ocean, but you can only see out to where the Earth's curvature hides the water beyond the horizon. You know there's more ocean out there, but you can't directly observe it. Our cosmic situation is remarkably similar, except the horizon isn't created by planetary curvature, but by the limits of how far light has been able to travel since the Big Bang. This observable universe contains roughly 2 trillion galaxies, each harboring billions of stars and potentially countless planets. The numbers are so vast they strain human comprehension. Yet according to multiverse theories, this incomprehensibly large realm might represent an infinitesimally small fraction of what actually exists. It's like discovering that what you thought was the entire ocean is actually just a single drop of water in an endless sea. The scientific foundation for these ideas emerged in the 1980s with the development of cosmic inflation theory. Alan Guth, then a young physicist at MIT, was grappling with some puzzling problems in Big Bang cosmology. Why was the universe so remarkably flat and uniform when basic physics suggested it should be curved and lumpy? Why did distant regions of space that had never been in contact with each other have nearly identical temperatures? Guth's solution was elegant and revolutionary. He proposed that in the first tiny fraction of a second after the Big Bang, space itself underwent a period of exponential expansion called inflation. During this brief epoch, a region smaller than a proton expanded to cosmic proportions faster than the speed of light. This rapid stretching smoothed out any initial irregularities and created the flat, uniform universe we observe today. But here's where the story takes an extraordinary turn. Once physicists began studying inflation in detail, they discovered something remarkable and unsettling. The same quantum fluctuations that ended inflation in our region of space would have different effects elsewhere. While inflation stopped here, creating our Big Bang and allowing galaxies and stars, it would continue matter and energy to condense into in other regions, spawning new inflating domains that would eventually undergo their own Big Bang-like transitions. This process, called eternal inflation, suggests that our universe is just one bubble in an eternally expanding multiverse. New universes are constantly being born as quantum fluctuations trigger the end of inflation in different regions of space. Each of these bubble universes would be causally disconnected from all the others, evolving according to its own physical laws and containing its own unique arrangement of matter and energy. Andre Linde, one of the architects of inflation theory, describes this scenario in almost poetic terms. Instead of a universe with a single law of physics, eternal chaotic inflation predicts a self-reproducing, eternally existing multiverse where all possibilities can be realized. In some other universe, he suggests, you are reading these very words right now. Not someone similar to you, but you yourself, living in a cosmos identical to ours down to the quantum level. In yet another universe, the history of Earth unfolded differently, perhaps with dinosaurs never going extinct, or with entirely different evolutionary pathways leading to unimaginable forms of life. The mathematics underlying eternal inflation are both beautiful and terrifying in their implications. If the theory is correct, then everything that can happen will happen, not just once but infinitely many times across the vast ensemble of bubble universes. Every possible arrangement of atoms, every potential outcome of quantum events, every conceivable variation of physical laws gets realized somewhere in the multiverse. This connects to one of the most perplexing mysteries in cosmology, the fine-tuning problem. The fundamental constants of nature, from the strength of gravity to the mass of the electron, appear to be precisely calibrated to allow for the formation of stars, planets, and ultimately life. Change any of these constants by even a small amount, and the universe becomes sterile, unable to support the complex chemistry necessary for biology. In a single universe scenario, this fine-tuning seems to require either extraordinary coincidence or intelligent design. But in a multiverse populated by bubble universes with different physical properties, fine-tuning becomes a selection effect. We observe constants that permit life, not because they were specially chosen, but because we could only have evolved in a universe where such constants allow for our existence. The vast majority of universes in the multiverse might be empty and lifeless, but observers can only exist in the tiny fraction where conditions happen to be just right. This anthropic reasoning has sparked intense debate within the physics community. Some researchers embrace it as an elegant solution to the fine-tuning problem, while others see it as an abandonment of the traditional goal of finding unique, predictive theories. The controversy touches on fundamental questions about the nature of scientific explanation and the role of observers in determining physical reality. Meanwhile, an entirely different pathway to the multiverse emerges from quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. Since its development in the early 20th century, quantum mechanics has revealed a reality far stranger than our everyday experience suggests. Particles exist in multiple states simultaneously until measured, becoming entangled across vast distances in ways that Einstein famously called spooky action at a distance. The strangeness of quantum mechanics led Hugh Everett III to propose a radical reinterpretation in 1957. Rather than accepting that quantum measurements cause wave functions to mysteriously collapse into single outcomes, Everett suggested that all possible outcomes actually occur simultaneously in parallel branches of reality. This many worlds interpretation eliminates the arbitrary boundary between quantum and classical physics by treating everything as fundamentally quantum mechanical. In Everett's vision, every quantum interaction throughout the universe constantly splits reality into multiple branches. Each possible outcome of every quantum measurement gets realized in a different branch, creating an ever-growing tree of parallel worlds. These worlds are completely real, but forever isolated from one another, making direct communication or travel between them impossible. The scale of branching in the many worlds interpretation is truly staggering. As Max Tegmark of MIT puts it, all possible states exist at every instant. Every quantum transition taking place on every star, in every galaxy, in every remote corner of the universe, splits our local reality into countless copies. The number of parallel worlds grows exponentially with each passing moment, creating an unimaginably vast ensemble of realities where every possible version of history unfolds. This quantum multiverse operates on completely different principles than the bubble universes of eternal inflation. While inflating bubbles are separated by physical space and evolving under potentially different laws of physics, the many worlds of quantum mechanics are superimposed in the same space but isolated by the fundamental structure of quantum reality itself. They represent different branches of the universal wave function, each as real and complete as our own observed reality. String theory, physics' most ambitious attempt to unify all fundamental forces into a single theoretical framework, contributes its own version of the multiverse through what researchers call the string landscape. String theory requires additional spatial dimensions beyond the three we observe, and these extra dimensions must be compactified or curled up in ways that remain hidden at everyday scales. The mathematical complexity of string theory allows compactification, each leading to different for an astronomical number of ways to accomplish this physical laws and constants in the resulting four-dimensional universe. Current estimates suggest the number of possible string theory vacua could be roughly 10 to the power of 500,000 or higher, creating what Leonard Susskind calls a vast landscape of possible universes. When combined with eternal inflation, the string landscape suggests that different regions of the multiverse settle into different string theory configurations, creating bubble universes with dramatically different physical properties. Some might have stronger or weaker forces, different numbers of particle types, or even different dimensional structures. This provides another potential explanation for the fine-tuning of our universe, with all possible values of physical constants being realized somewhere across the landscape of possibilities. Yet despite decades of theoretical development and increasingly sophisticated mathematical frameworks, the multiverse remains one of the most controversial ideas in modern physics. The fundamental challenge is observational. By definition, other universes exist beyond our cosmic horizon or in parallel quantum branches we can never directly access. This apparent untestability has led some critics to argue that multiverse theories venture beyond the bounds of legitimate science into the realm of metaphysics. The debate touches on deep philosophical questions about the nature of scientific knowledge itself. Traditional approaches to science emphasize the importance of making testable predictions that can be verified or falsified through observation and experiment. But multiverse theories appear to violate this principle by making claims about entities that may be fundamentally unobservable. Some physicists have responded by developing new approaches to evaluating theories that cannot be directly tested. They focus on explanatory power, mathematical consistency, and the ability to make predictions about observable phenomena, even when the theory itself invokes unobservable entities. Others remain deeply skeptical, arguing that without empirical contact, these ideas cease to be physics and become something closer to philosophy or mathematics. The search for evidence has led scientists to examine subtle patterns in the cosmic microwave background radiation, the ancient light left over from when our universe was only 380,000 years old. Researchers have looked for signatures that might indicate collisions with other bubble universes, unusual correlations that might suggest quantum entanglement between different branches of reality, or statistical anomalies that deviate from single universe predictions. One particularly intriguing feature is the cosmic microwave background cold spot, an unusually large and cold region in the constellation Eridanus that appears to violate the statistical expectations of standard cosmology. Some researchers have speculated that this anomaly might represent evidence of interaction with another universe, though more conventional explanations involving supervoids and gravitational effects remain favoured by most scientists. The stakes in this debate couldn't be higher. If multiverse theories are correct, they would fundamentally transform our understanding of reality, suggesting that our observable universe represents just one thread in an infinite tapestry of existence. Every question about why the universe has the properties it does would need to be reframed in terms of observer selection effects across an ensemble of realities. The very meaning of existence, uniqueness, and cosmic significance would require complete reconceptualization. But the implications extend far beyond abstract philosophy into the practical realm of how science should proceed. If we accept that some aspects of reality may be forever beyond direct observation, how do we maintain scientific rigor? How do we distinguish between legitimate theoretical speculation and untestable metaphysics? These questions challenge the foundations of the scientific method itself. The experimental search for multiverse signatures has pushed observational cosmology to its absolute limits, forcing scientists to develop increasingly sophisticated techniques for detecting phenomena that may be fundamentally beyond direct observation. At observatories around the world, researchers pore over cosmic microwave background data, with the intensity of detectives examining evidence at a crime scene, searching for the faintest hints that our universe might have once brushed against another reality. Stephen Feeney and his colleagues at University College London made headlines in 2010 when they claimed to have found circular patterns in the cosmic microwave background that could represent scars from collisions with neighbouring bubble universes. These features, if real, would appear as subtle temperature variations imprinted on the ancient light that fills all of space. The team developed sophisticated algorithms to search through millions of data points, looking for the specific geometric signatures that theoretical models predicted such collisions would leave behind. The analysis was extraordinarily complex, requiring the researchers to account for countless sources of contamination and systematic error. Galactic foregrounds, instrumental noise, and the natural statistical fluctuations in the cosmic microwave background all conspired to hide any potential multiverse signatures. Yet when the dust settled, Feeney's team reported finding several candidate features that matched the expected properties of bubble collisions with statistical significance that seemed to rule out pure chance. The announcement sent ripples of excitement through the cosmology community, but the euphoria was short-lived. More detailed analysis using data from the European Space Agency's Planck satellite, with resolution 3 times higher than previous missions, failed to confirm the claimed detections. The circular patterns that had seemed so promising dissolved into statistical noise when examined with greater precision. The search had pushed the boundaries of what could be extracted from observational data, but it had not quite breached the barrier separating our universe from others. This pattern of initial excitement, followed by careful refutation, has characterized much of the empirical search for multiverse evidence. In 2015, another team claimed to have found anomalous patterns in the cosmic microwave background that might indicate quantum entanglement between our universe and others. The researchers suggested that correlations between widely separated regions of the sky might reflect the quantum mechanical connections that existed before cosmic inflation separated different regions into causally disconnected universes. The proposal was ingenious, building on the fundamental principles of quantum mechanics to predict observable consequences of multiverse theories. If regions of our observable universe had once been quantum mechanically entangled with regions now existing in other bubble universes, then subtle correlations might persist in the cosmic microwave background radiation. These quantum fossils would provide a direct window into the multiverse, preserved in the most ancient light we can observe. Yet once again, independent analysis failed to confirm the claimed detections. The correlations that had seemed significant in initial studies proved to be consistent with the natural statistical variations expected in a single universe. The search for quantum entanglement signatures joined the growing list of tantalizing possibilities that had not survived rigorous scrutiny. These failures have not discouraged researchers from continuing the hunt for multiverse evidence. Instead, they have driven the development of increasingly sophisticated theoretical frameworks for predicting what signatures other universes might leave in observable phenomena. Theorists have proposed that bubble universe collisions could create not only circular patterns in the cosmic microwave background, but also preferential alignments of galaxy distributions, unusual properties of gravitational waves, or anomalous features in the large-scale structure of the cosmos. The search has also expanded beyond the cosmic microwave background to encompass other observational windows into the early universe. The detection of gravitational waves by facilities like LIGO and Virgo has opened entirely new possibilities for probing fundamental physics. Some researchers have suggested that collisions between bubble universes might generate distinctive gravitational wave signatures that could be detected by current or future observatories. Advanced LIGO has already detected dozens of gravitational wave events from merging black holes and neutron stars, providing unprecedented insight into extreme gravitational phenomena. The data from these detections is being scrutinized for any anomalous features that might indicate interactions with other universes or deviations from general relativity that could support multiverse theories. While no definitive signatures have been identified, the field is still in its infancy, with much more sensitive detectors planned for the coming decades. The European Space Agency's upcoming LISA mission will place gravitational wave detectors in space, providing access to entirely different frequency ranges than ground-based facilities. These space-based observatories could potentially detect gravitational waves from the early universe itself, including any signatures left by the process of eternal inflation that creates bubble universes. The possibility of directly observing the birth of other universes through gravitational radiation represents one of the most exciting prospects in multiverse research. Meanwhile, the Large Hadron Collider and other particle physics experiments continue to probe the fundamental structure of matter and energy at the smallest scales. Some theoretical models suggest that evidence for extra dimensions or string theory could provide indirect support for multiverse scenarios. The discovery of additional spatial dimensions, new fundamental particles, or unexpected symmetries in the laws of physics could all strengthen the case for theories that naturally lead to multiverse predictions. The search for dark matter, which comprises roughly 85% of all matter in the universe, has also taken on new significance in the context of multiverse theories. Some models suggest that dark matter could consist of particles that interact primarily through gravitational forces, making them nearly invisible to ordinary matter. If such particles exist, they might provide a window into the fundamental physics underlying multiverse scenarios, particularly those involving extra dimensions or exotic particle physics. Underground laboratories around the world are conducting increasingly sensitive searches for dark matter particles, using detectors buried deep beneath the Earth's surface to shield them from cosmic radiation. The most advanced experiments can detect the recoil of atomic nuclei from dark matter collisions, with sensitivity approaching the theoretical limits imposed by quantum mechanics. While no definitive dark matter detections have been confirmed, the ongoing searches continue to constrain theoretical models and could potentially reveal new physics relevant to multiverse scenarios. The interplay between particle physics and cosmology has become increasingly important as researchers recognize that understanding the multiverse requires knowledge of physics at both the largest and smallest scales. The fundamental forces and particles that govern interactions in laboratory experiments also determine the properties of entire universes across the multiverse landscape. This connection has led to the development of new interdisciplinary approaches that combine insights from high-energy physics, cosmology, and quantum field theory. String theorists have played a particularly important role in developing these connections, using mathematical tools from quantum field theory to study both the microscopic structure of fundamental particles and the macroscopic evolution of entire universes. The string landscape emerges from detailed calculations of how extra dimensions can be compactified in different ways, with each configuration corresponding to a different set of physical laws and constants. The mathematical complexity of these calculations is staggering, involving advanced techniques from algebraic geometry, topology, and mathematical physics. Researchers must navigate through abstract mathematical spaces with hundreds or thousands of dimensions, mapping out the landscape of possible universes and determining which configurations are stable enough to support long-lived cosmic evolution. The number of possible configurations grows exponentially with the complexity of the compactification scheme, leading to the vast ensemble of possibilities that characterizes the string landscape. Leonard Susskind, one of the founders of string theory, has become a leading advocate for the Anthropic approach to understanding this landscape. In his view, the enormous number of possible string theory vacua naturally explains the apparent fine-tuning of physical constants in our universe. Rather than requiring special initial conditions or intelligent design, the fine-tuning emerges from observer selection effects across the vast ensemble of possibilities. This anthropic reasoning has profound implications for how we understand the goals and methods of theoretical physics. Traditionally, physicists have sought theories that make unique, testable predictions about observable phenomena. The discovery of quantum mechanics, relativity, and the standard model of particle physics all followed this pattern, with theoretical developments leading to specific experimental predictions that could be verified or falsified. But the string landscape suggests a different approach, where theories predict not unique outcomes, but probability distributions across ensemble of possibilities. In this framework, the goal of physics becomes understanding which types of universes are more common in the multiverse and calculating the probability that observers like ourselves would find themselves in a universe with specific properties. This shift toward probabilistic reasoning has generated intense controversy within the physics community. Critics argue that anthropic explanations are inherently untestable and therefore unscientific. They worry that accepting anthropic reasoning could lead to abandonment of the search for deeper, more fundamental explanations of why the universe has the properties it does. Supporters counter that anthropic reasoning has already proven successful in making testable predictions. They point to cases where anthropic arguments correctly predicted the observed value of the cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe. Steven Weinberg used anthropic reasoning in the 1980s to predict that the cosmological constant should be small but positive, a prediction that was dramatically confirmed by observations of distant supernova in the 1990s. The cosmological constant represents one of the most severe fine-tuning problems in physics. Quantum field theory predicts that empty space should have an enormous energy density, roughly 10 to the power of 120 times larger than what observations indicate. This discrepancy represents the worst theoretical prediction in the history of science, suggesting that our understanding of quantum mechanics, general relativity, or both, must be fundamentally incomplete. In a single universe scenario, explaining why the cosmological constant has its observed value requires either extraordinary fine-tuning or completely new physics. But in a multiverse where different regions of space can have different values of the cosmological constant, the observed value becomes a selection effect. Universes with large positive cosmological constants expand so rapidly that matter never condenses into galaxies and stars. Universes with large negative cosmological constants collapse before complex structures can form. Only universes with cosmological constants close to zero allow for the formation of the galaxies, stars, and planets necessary for the emergence of observers. This anthropic explanation for the cosmological constant has been remarkably successful, correctly predicting the magnitude and sign of the observed value years before it was measured. The success has encouraged researchers to apply similar reasoning to other fine-tuning problems, from the strength of fundamental forces to the properties of elementary particles. Yet the anthropic approach raises troubling questions about the nature of scientific explanation and prediction. If we accept that some features of our universe result from selection effects across a multiverse ensemble, how do we distinguish between genuine predictions and post hoc explanations? How do we maintain scientific rigor when dealing with theories that invoke fundamentally unobservable entities? These questions have led to the development of new philosophical frameworks for evaluating theories that transcend traditional empirical boundaries. Some philosophers of science have proposed criteria based on explanatory power and mathematical consistency rather than direct testability. Others have argued for a more pragmatic approach, focusing on whether theories make successful predictions about observable phenomena, regardless of whether their underlying assumptions can be directly verified. The debate has been complicated by the recognition that even our most successful theories routinely invoke unobservable entities. Quarks, the fundamental constituents of protons and neutrons, cannot be isolated and observed directly due to the nature of the strong nuclear force. Yet their existence is universally accepted because of the successful predictions of quantum chromodynamics, the theory that describes their interactions. Similarly, the Higgs boson existed only as a theoretical concept for nearly 50 years before being detected at the Large Hadron Collider. The multiverse theories differ from these examples primarily in the scale of their unobservable elements. While individual quarks or Higgs bosons cannot be directly observed, their collective effects can be measured in laboratory experiments. Other universes, by contrast, may be fundamentally beyond the reach of any possible observation or experiment. This difference in observational accessibility has become a central point of contention in evaluating the scientific legitimacy of multiverse theories. Some researchers have responded by developing new approaches to testing multiverse theories that focus on their observable consequences rather than their unobservable assumptions. These indirect tests examine whether multiverse theories make successful predictions about phenomena we can observe, such as the statistical properties of the cosmic microwave background, the distribution of galaxies on large scales, or the fundamental constants of particle physics. The cosmic microwave background has emerged as perhaps the most important testing ground for these indirect approaches. This ancient radiation carries information about the conditions in our universe when it was only 380,000 years old, providing a detailed snapshot of cosmic evolution at a crucial epoch. Any interactions with other universes or exotic physics associated with multiverse scenarios might leave subtle imprints in this primordial light. Advanced statistical techniques have been developed to extract every possible bit of information from cosmic microwave background data. Machine learning algorithms search for patterns that human researchers might miss, while sophisticated theoretical models predict what signatures different multiverse scenarios should produce. The European Space Agency's Planck satellite has provided the most detailed maps of the cosmic microwave background ever obtained, with sensitivity approaching the fundamental limits imposed by cosmic variance. Yet despite extraordinary advances in both observational capability and theoretical sophistication, the cosmic microwave background has revealed no definitive evidence for multiverse phenomena. The radiation appears remarkably consistent with the predictions of standard single-universe cosmology, with only minor deviations that can be explained by conventional astrophysical processes. This absence of clear multiverse signatures has led some researchers to conclude that other universes, if they exist, have left no detectable traces in our observable cosmos. The isolation between different regions of the multiverse may be so complete that no information can flow between them, making empirical verification fundamentally impossible. Others maintain that the search has only just begun, and that future observations with more sensitive instruments might reveal the subtle signatures that current technology cannot detect. The next generation of cosmic microwave background experiments, ground-based telescopes studying the large-scale structure of the universe, and space-based gravitational wave detectors all offer new possibilities for testing multiverse theories. The James Webb Space Telescope, now operational and providing unprecedented views of the early universe, represents another potential window into multiverse physics. By observing the most distant galaxies ever detected, Webb is probing cosmic epochs that may preserve information about the fundamental processes that gave rise to our universe. If eternal inflation or other multiverse mechanisms played a role in cosmic origins, their signatures might be visible in the properties of the earliest galactic structures. The search for multiverse evidence has also inspired the development of entirely new theoretical frameworks that could make more specific predictions about observable phenomena. Some researchers have proposed that different regions of the multiverse might be connected by traversable wormholes or other exotic space-time structures that could allow limited information transfer between universes. While such connections would still fall far short of direct observation, they might create detectable anomalies in the distribution of matter and energy in our universe. Other theoretical approaches focus on the quantum mechanical aspects of multiverse theories, particularly the many worlds interpretation of quantum mechanics. Some researchers have suggested that subtle correlations between quantum measurements might reveal information about parallel branches of reality, though the practical challenges of detecting such correlations appear enormous. The field of quantum computing has provided new tools for exploring these quantum mechanical aspects of multiverse theories. David Deutsch, one of the pioneers of quantum computation, has argued that quantum computers derive their extraordinary power from performing calculations across multiple parallel worlds simultaneously. If correct, this interpretation suggests that we are already harnessing the computational resources of the multiverse, even if we cannot directly observe other realities. Quantum computers have successfully demonstrated the ability to solve certain problems exponentially faster than classical computers, apparently by exploring vast numbers of solution paths simultaneously through quantum superposition. The mathematical description of these quantum algorithms bears striking resemblances to the many worlds interpretation, where different branches of reality explore different computational pathways before converging on the final answer. While this connection between quantum computing and parallel worlds remains speculative, it illustrates how multiverse theories continue to influence cutting-edge research in physics and computer science. The boundaries between theoretical speculation and practical application become increasingly blurred as our understanding of quantum mechanics deepens and our technological capabilities advance. The implications of these developments extend far beyond academic physics into questions about the fundamental nature of reality and our place within it. If multiverse theories are correct, they would require us to reconceptualize almost everything we think we know about existence, uniqueness, and cosmic significance. Our entire observable universe, with its rich history of stellar evolution, galactic formation, and biological development, would represent just one small chapter in an infinite cosmic library. The profound philosophical implications ripple outward, like waves in a cosmic pond, touching every aspect of how we understand meaning, purpose, and identity in an infinite multiverse. Consider what it means to be unique, when there might be countless identical copies of yourself scattered across bubble universes, each living lives that diverge at different quantum decision points. In some realities, you never picked up this video tonight. In others, you became a physicist yourself, dedicating your life to unraveling these very mysteries we're exploring together. Max Tegmark of MIT has spent decades contemplating these existential puzzles. In his mathematical universe hypothesis, he suggests that all mathematically consistent structures exist as physical realities somewhere in the ultimate multiverse. This isn't just the bubble universes of eternal inflation or the parallel branches of quantum mechanics, but every possible mathematical framework that could describe a self-consistent reality. Universes where mathematics itself operates differently, where logic follows alternate rules, where the very concept of existence takes forms we cannot even imagine. Tegmark describes this as a four-level hierarchy of multiverses, each more exotic than the last. Level 1 encompasses the regions beyond our observable horizon, containing more of the same physics, but different arrangements of matter. Level 2 includes the bubble universes of eternal inflation, with potentially different physical laws and constants. Level 3 represents the parallel branches of quantum mechanics, where all possible outcomes of quantum events are realized. And Level 4, the most speculative, contains all possible mathematical structures as physical realities. The mathematical universe hypothesis pushes the boundaries of what we might consider physics versus philosophy. If every logically consistent mathematical structure corresponds to a physical universe, then abstract concepts like numbers, geometric shapes, and algebraic equations become as real as the stars and planets we observe. We wouldn't just live in a mathematical universe. We would be mathematical structures, patterns of information processing within a vast computational multiverse. This perspective transforms how we think about the relationship between mind and mathematics. When you contemplate a geometric theorem or solve an equation, you might be directly interfacing with the mathematical structures that constitute reality itself. Consciousness wouldn't emerge from material processes, but would represent the universe's method of exploring its own mathematical nature through self-aware information patterns. Yet even as these theories push toward the limits of human comprehension, physicists continue developing new frameworks for testing their implications. The holographic principle, discovered through studies of black hole physics, suggests that all the information contained within any volume of space can be encoded on its two-dimensional boundary. This remarkable idea emerged from attempts to resolve paradoxes about what happens to information that falls into black holes, but its implications extend far beyond gravitational physics. Leonard Susskind and Gerard 't Hooft independently developed the holographic principle in the 1970s and 80s, showing that the three-dimensional interior of any region can be completely described by information stored on its two-dimensional surface. This isn't just a mathematical trick, but reflects something fundamental about the nature of space, time, and information itself. The holographic principle has profound implications for multiverse theories. If our three-dimensional reality is actually encoded on a distant two-dimensional surface, then the distinction between simulation and reality becomes meaningless. We might be holographic projections of information, processing occurring in dimensions we cannot directly perceive. The richness and complexity of our experienced reality would emerge from quantum computations happening on the cosmic horizon, the boundary of our observable universe. Juan Maldacena's discovery of the anti-de Sitter conformal field theory correspondence in 1997 provided concrete mathematical realization of holographic principles. His work showed that a theory of quantum gravity in a higher dimensional anti-de Sitter space is mathematically equivalent to a quantum field theory on its lower dimensional boundary. This holographic duality has become one of the most important developments in theoretical physics, providing new tools for understanding both quantum gravity and strongly interacting quantum systems. The anti-de Sitter conformal field theory correspondence suggests that the gravitational physics we experience might be the holographic shadow of quantum field theories operating in higher dimensions. Particles, forces, and even space-time itself would be emergent properties of more fundamental information processing occurring beyond our direct perception. This holographic emergence provides yet another pathway to multiverse scenarios where different boundary theories could give rise to different bulk space-time realities. These holographic ideas are influencing how researchers think about the fundamental nature of reality. Rather than space and time being fundamental, they might be emergent properties of more basic information processing. The universe wouldn't be made of matter and energy moving through space, but of quantum information being processed according to mathematical rules that create the appearance of physical reality. This information-theoretic approach to physics has gained momentum through developments in quantum computing and quantum information theory. Researchers have discovered that many of the most important quantities in physics, from black hole entropy to the curvature of spacetime, can be expressed in terms of quantum information. The universe begins to look less like a mechanical system and more like a vast quantum computer, processing information on scales from the subatomic to the cosmic. The connection between information and multiverse theories becomes particularly intriguing when we consider the role of observation and measurement. In quantum mechanics, the act of observation appears to play a fundamental role in determining which possibilities become actualized. If consciousness represents a form of information processing, then observers might not just be passive witnesses to reality, but active participants in the cosmic computation that generates physical existence. This observer-participatory universe concept, developed by John Wheeler and others, suggests that the act of asking questions about reality helps to create the reality we observe. In a multiverse context, conscious observers might serve as the mechanism that selects which branch of reality becomes experienced, navigating through the infinite tree of possibilities that quantum mechanics generates. The implications extend to questions about the origin and ultimate fate of the multiverse itself. If realities can branch and merge through quantum processes, then the multiverse might not be static, but dynamically evolving, with new types of universes constantly emerging while others fade away. Some researchers have speculated about cosmological natural selection, where universes that produce black holes create offspring universes through quantum tunneling processes, leading to the evolution of multiverse populations over cosmic time. Lee Smolin has developed this idea into a comprehensive theory called cosmological natural selection, suggesting that universes with physical constants that favor black hole formation are more likely to reproduce and pass their properties to descendant universes. Over vast timescales, the multiverse would evolve toward configurations that maximize black hole production, potentially explaining why our universe has physical constants that allow for stellar collapse and black hole formation. This evolutionary approach to multiverse theory provides a naturalistic explanation for apparent fine-tuning without invoking anthropic reasoning. instead of requiring that physical constants be specially chosen to permit observers. Cosmological natural selection suggests that these constants evolved through a process analogous to biological evolution, with successful universes reproducing more frequently than unsuccessful ones. The theory makes specific predictions about the properties we should observe in our universe, particularly regarding the masses of elementary particles and the strength of fundamental forces. These predictions can be tested against observations, providing a potential way to evaluate the theory's validity without directly observing other universes. Yet even these evolutionary multiverse theories face the challenge of explaining how the first universes came into existence. If new universes are born from black holes in existing universes, what created the original parent universe that started the entire process? This regression problem appears in many multiverse scenarios, suggesting that understanding cosmic origins might require concepts that transcend our current frameworks entirely. Some researchers have proposed that the multiverse might be eternal and self-creating, with no beginning or end in conventional time. In these scenarios, the question of ultimate origins becomes meaningless because time itself is an emergent property of local physics, rather than a universal backdrop against which events occur. Different regions of the multiverse might have their own local time coordinates, with no global temporal ordering that would allow us to identify a moment of creation. The search for experimental signatures of these exotic multiverse scenarios continues to push observational cosmology toward new frontiers. The cosmic microwave background polarization experiments, like BICEP and Planck, are searching for the subtle spiraling patterns that primordial gravitational waves would imprint on ancient light. These gravitational waves, if detected, would provide direct evidence for the inflationary epoch that potentially gave birth to our bubble universe. The European Space Agency's upcoming Euclid mission will map the distribution of dark matter and dark energy across billions of galaxies, potentially revealing signatures of interactions with other universes or exotic physics associated with multiverse scenarios. The mission will create the most detailed three-dimensional map of cosmic structure ever attempted, providing unprecedented insight into the fundamental forces shaping our universe. Ground-based telescopes are also contributing to this search through increasingly sensitive observations of distant supernova, galaxy clusters, and other cosmic phenomena. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky repeatedly for 10 years, potentially discovering subtle anomalies that could point toward multiverse physics. These observational programs are complemented by advances in theoretical modeling and computer simulation. Researchers are developing increasingly sophisticated models of how multiverse interactions might manifest in observable phenomena, creating detailed predictions that can be tested against real data. Supercomputer simulations explore how bubble universes might collide and what signatures such collisions would leave in cosmic microwave background radiation. Machine learning and artificial intelligence are also being deployed in the search for multiverse evidence. Neural networks trained on theoretical predictions can search through vast astronomical datasets, identifying patterns that human researchers might miss. These AI systems are particularly valuable for detecting subtle correlations or anomalies that might indicate interactions with other universes. The international collaboration required for these searches has created new models for scientific cooperation that transcend traditional boundaries. Researchers from dozens of countries contribute to experiments like the Large Hadron Collider and the Laser Interferometer Gravitational Wave Observatory, pooling resources and expertise to tackle questions that no single institution could address alone. This global scientific enterprise reflects the profound human drive to understand our cosmic context regardless of whether that context includes other universes beyond our own. The search for the multiverse has pushed us to develop new technologies, mathematical techniques, and philosophical frameworks that advance human knowledge in countless ways, even as the ultimate questions remain tantalizingly beyond our reach. The next generation of experiments and observations will provide unprecedented sensitivity to the subtle signatures that multiverse theories predict. The James Webb Space Telescope is already revealing details about the earliest galaxies that formed in our universe, potentially preserving information about the cosmic conditions that gave rise to our bubble of reality. Future gravitational wave detectors in space will probe the fundamental structure of space-time itself, perhaps detecting the remnants of cosmic inflation or interactions between parallel universes. Quantum computing advances are opening new possibilities for testing the many worlds interpretation through increasingly sophisticated quantum information experiments. As these systems become more powerful and controlled, they might reveal correlations or effects that provide evidence for parallel quantum realities processing information alongside our own. Yet even as technology advances and theories become more sophisticated, the fundamental challenge of observing the unobservable remains. The multiverse, if it exists, might be forever beyond direct detection, accessible only through its subtle influences on the reality we can observe. This limitation forces us to grapple with profound questions about the nature of scientific knowledge and the boundaries of human understanding. Perhaps the greatest gift of multiverse theories isn't their potential truth, but their role in expanding our conception of what might be possible. They challenge us to think beyond the familiar confines of our observable universe, to consider possibilities that stretch the imagination while remaining grounded in rigorous mathematics and careful observation. In contemplating infinite realities where every possibility is realized, we gain perspective on the preciousness and contingency of our own existence. Every choice, every moment of consciousness, every experience of beauty or wonder becomes part of a vast cosmic story that encompasses not just our universe, but potentially all possible universes that mathematical consistency allows. Whether the multiverse exists as a physical reality or remains a theoretical construct, it serves as a mirror reflecting our deepest questions about existence, meaning, and our place in the grand scheme of things. The search for other universes ultimately becomes a search for understanding ourselves and the nature of reality itself, a quest that pushes the boundaries of human knowledge toward horizons we are only beginning to glimpse. The question of whether we will ever definitively prove the existence of other universes brings us face to face with the fundamental limits of scientific knowledge itself. As we drift deeper into these conceptual waters, we encounter something both humbling and profound. The very theories that predict the multiverse also suggest why it might remain forever beyond our direct reach. Consider the observational challenges that confront any attempt to detect other universes. The cosmic microwave background radiation represents our most ancient observable light, carrying information from when our universe was merely 380,000 years old. This primordial glow has travelled through space for over 13 billion years to reach our telescopes tonight, and it may contain the only accessible evidence of what happened during the universe's first moments. Dr. Rangaram Chari at the California Institute of Technology spent years developing new statistical techniques to analyze this ancient radiation. His work focused on detecting what he calls anomalous emission that might indicate interactions with neighboring bubble universes. The mathematics involved are staggering in their complexity, requiring the analysis of millions of data points while accounting for countless sources of contamination and systematic error. Chari's team discovered something intriguing. Embedded within the cosmic microwave background's seemingly random fluctuations, they found patterns that appeared too organized to result from purely random processes. These patterns manifested as subtle temperature variations that seemed to align in ways that violated the statistical expectations of standard cosmology. The alignments were faint, requiring extraordinary precision to detect, but they persisted across multiple independent analyses. The discovery sparked intense debate within the cosmology community. Some researchers suggested these patterns might represent the gravitational influence of matter in other universes, creating subtle distortions in the fabric of space-time that would appear as temperature variations in the cosmic microwave background. Others proposed they might indicate regions where our bubble universe had brushed against neighbouring bubbles during the epoch of cosmic inflation. Yet skeptics pointed out that extraordinary claims require extraordinary evidence, and the patterns Chari's team detected remained tantalizingly close to the noise level of current instruments. Independent research groups attempted to verify the findings using different analysis techniques and datasets, but the results remained ambiguous. Some confirmatory evidence emerged, while other studies found no significant deviations from random expectations. This pattern of tentative detection, followed by inconclusive verification, has characterized much of the observational search for multiverse evidence. The phenomena we seek exist at the very limits of what current technology can measure, buried beneath layers of cosmic noise and systematic uncertainties that make definitive conclusions extraordinarily difficult to reach. Laura Mersina Houghton at the University of North Carolina has approached the problem from an entirely different angle, focusing on what she calls quantum entanglement fossils. Her theory suggests that before cosmic inflation separated different regions into causally disconnected universes, these regions were quantum mechanically entangled. Even after inflation stretched them beyond any possibility of communication, subtle correlations might persist as observable signatures in the cosmic microwave background. Mersini Houghton's predictions are mathematically precise and potentially testable. She has identified specific patterns that quantum entanglement between universes should produce in the polarization of cosmic microwave background radiation. These patterns would manifest as correlations between regions of the sky that have never been in causal contact, creating what she describes as spooky action at a cosmic distance. The European Space Agency's Planck satellite collected data with sufficient precision to test some of Mersini Houghton's predictions, and initial results showed tantalizing hints of the predicted correlations. However, as with previous claimed detections, independent verification proved elusive. The signals were weak, the analysis complex, and alternative explanations involving conventional astrophysical processes could not be definitively ruled out. These observational challenges have led some researchers to explore entirely different approaches to testing multiverse theories. Rather than searching for direct signatures of other universes, they focus on testing the theoretical frameworks that predict multiverse scenarios. If eternal inflation theory or the many worlds interpretation of quantum mechanics can be verified through other means, then their multiverse implications gain credibility even without direct detection of parallel realities. This indirect approach has proven remarkably fruitful. The discovery of the Higgs boson at the Large Hadron Collider confirmed key predictions of the standard model of particle physics, lending support to quantum field theories that naturally lead to multiverse scenarios. Gravitational wave detections by LIGO and Virgo have verified Einstein's general relativity with unprecedented precision, strengthening our confidence in the theoretical frameworks underlying cosmic inflation. Meanwhile, advances in quantum computing are providing new ways to test the many worlds interpretation. David Deutsch argues that quantum computers derive their computational power from performing calculations across multiple parallel worlds simultaneously. If this interpretation is correct, then every quantum computation provides indirect evidence for the existence of parallel realities. The quantum supremacy experiments conducted by Google and other research groups have demonstrated quantum computers solving specific problems exponentially faster than classical systems. While alternative explanations for this speed-up exist, the many worlds interpretation offers a particularly elegant account of where the computational resources come from. Each quantum bit exists in superposition across multiple parallel worlds, allowing the quantum computer to explore vast numbers of solution paths simultaneously before converging on the final answer. Yet even these indirect approaches face fundamental limitations. The many worlds interpretation makes no unique predictions that distinguish it from other interpretations of quantum mechanics. All interpretations reproduce the same experimental results, making them empirically equivalent despite their radically different implications for the nature of reality. This equivalence problem extends to multiverse theories more generally. Eternal inflation, the many worlds interpretation, and string theory landscapes all make similar predictions about observable phenomena while invoking vastly different underlying realities. Without unique observational signatures, these theories remain mathematically consistent but empirically underdetermined. Some philosophers of science argue that this underdetermination doesn't invalidate multiverse theories, but rather reflects the inherent limitations of empirical investigation when dealing with phenomena that transcend direct observation. They propose alternative criteria for evaluating theories, focusing on explanatory power, mathematical elegance, and consistency with established physics, rather than direct testability. Sean Carroll at the California Institute of Technology has become a leading advocate for this broader conception of scientific validity. He argues that multiverse theories deserve serious consideration because they emerge naturally from our best understanding of fundamental physics. The theories aren't arbitrary speculations, but logical consequences of well-tested principles like quantum mechanics and general relativity. Carroll points out that science routinely accepts the existence of unobservable entities when they provide compelling explanations for observable phenomena. Electrons, quarks, and quantum fields cannot be directly observed, yet their existence is universally accepted because they successfully predict experimental results. Multiverse theories, he argues, deserve similar consideration when they provide elegant explanations for otherwise puzzling aspects of our universe. The fine-tuning problem provides perhaps the strongest motivation for taking multiverse theories seriously. The fundamental constants of nature appear precisely calibrated to allow for the existence of stars, planets, and ultimately life. The cosmological constant, the ratio of proton to electron masses, the strength of the strong nuclear force, and dozens of other parameters all lie within narrow ranges that permit complex structures to form. In a single universe, this fine-tuning seems to require either extraordinary luck or intelligent design. The probability that all these constants would randomly fall within life-permitting ranges is so vanishingly small that it strains credibility. Yet in a multiverse where different regions have different values of these constants, fine-tuning becomes a selection effect rather than a cosmic coincidence. Steven Weinberg demonstrated the power of this anthropic reasoning in the 1980s when he used multiverse arguments to predict the value of the cosmological constant. At the time, this quantity was unmeasured and theoretically problematic. Quantum field theory predicted it should be enormous, while observations suggested it was essentially zero. Weinberg realized that in a multiverse with varying cosmological constants, most universes would be uninhabitable. Large positive values would cause space to expand so rapidly that matter could never condense into galaxies and stars. Large negative values would cause universes to collapse before complex structures could form. Only universes with cosmological constants close to zero would allow for the formation of stars, planets, and observers. Based on this reasoning, Weinberg predicted that the cosmological constant should be small but positive, with a magnitude just barely consistent with galaxy formation. This prediction seemed speculative at the time, but it was dramatically confirmed in the 1990s when observations of distant supernova revealed that the expansion of our universe is indeed accelerating due to a small positive cosmological constant. The success of Weinberg's anthropic prediction has encouraged researchers to apply similar reasoning to other fine-tuning problems. Some have attempted to predict the masses of elementary particles, the strength of fundamental forces, and even the number of spatial dimensions based on anthropic arguments about what values would permit the existence of observers. However, anthropic reasoning faces significant challenges and criticisms. The approach requires assumptions about what types of observers are possible and what physical conditions are necessary for their existence. These assumptions may be biased by our limited understanding of life and consciousness, potentially leading to incorrect predictions about the range of habitable universes. Critics also argue that anthropic explanations are inherently post hoc, explaining observed phenomena after the fact rather than making genuine predictions that can be tested. While Weinberg's cosmological constant prediction appears genuinely predictive, many other anthropic arguments seem designed to explain existing observations rather than forecast new discoveries. Paul Steinhardt, one of the original architects of inflation theory, has become one of the most vocal critics of multiverse cosmology. He argues that eternal inflation has become unfalsifiable and therefore unscientific. The theory can accommodate any possible observation by invoking appropriate regions of the multiverse, making it impossible to test or potentially refute. Steinhardt's criticism touches on fundamental questions about the nature of scientific explanation and prediction. Traditional scientific theories make specific testable predictions about observable phenomena. They succeed by correctly forecasting new discoveries and fail when their predictions are contradicted by experiment. Multiverse theories, by contrast, seem to explain everything while predicting nothing unique. This debate over scientific methodology has divided the physics community into roughly two camps. One group, led by researchers like Sean Carroll, Max Tegmark, and Leonard Susskind, argues that multiverse theories represent legitimate extensions of established physics that deserve serious consideration despite their observational challenges. They emphasize the mathematical consistency of these theories and their ability to explain otherwise puzzling features of our universe. The opposing camp, including researchers like Sabine Hossenfelder, Paul Steinhardt, and George Ellis, maintains that physics must remain grounded in empirical observation and testable prediction. They argue that accepting untestable multiverse theories represents a dangerous departure from scientific methodology that could lead physics away from its empirical foundations toward pure mathematical speculation. This methodological debate reflects deeper tensions about the goals and nature of scientific inquiry. Is the purpose of science to describe observable phenomena as accurately as possible, or to uncover the fundamental nature of reality, even when that reality transcends direct observation? Can mathematical elegance and explanatory power substitute for empirical testability when dealing with phenomena that may be inherently unobservable? These questions become particularly acute when we consider the practical implications of multiverse research. The search for evidence of other universes has consumed significant resources and talented researchers who might otherwise contribute to more directly applicable areas of physics. Critics argue that this represents a misallocation of scientific effort, diverting attention from problems that could yield practical benefits for humanity. Supporters counter that fundamental physics has historically provided unexpected practical applications, from quantum mechanics enabling modern electronics to general relativity making GPS satellites possible. They argue that understanding the deeper structure of reality, even if that understanding involves unobservable multiverses, could lead to technological breakthroughs we cannot currently imagine. The debate also touches on the social and cultural role of science in providing meaning and context for human existence. Multiverse theories fundamentally alter how we think about our place in the cosmos, suggesting that our entire observable reality might represent an infinitesimal fraction of what actually exists. These implications extend far beyond academic physics into questions of philosophy, religion, and human purpose. Some find the multiverse concept liberating, suggesting that the apparent fine-tuning of our universe requires no special explanation or divine intervention. If all possible universes exist somewhere in the multiverse, then our particular combination of physical constants becomes unremarkable, simply one possibility among infinite others that happen to permit the existence of observers like ourselves. Others find multiverse theories deeply troubling, arguing that they drain significance from human existence by making our universe just one among countless others. If every possible version of history plays out somewhere in the multiverse, then our choices and actions lose their uniqueness and perhaps their meaning. The concept of moral responsibility becomes problematic when every possible decision is realized in some parallel reality. These philosophical implications have attracted attention from theologians, ethicists, and philosophers who grapple with the meaning of existence in a potentially infinite multiverse. Some have argued that multiverse theories are compatible with the religious worldviews, simply expanding the scope of creation to encompass all possible realities. Others contend that infinite multiverses eliminate the need for divine creation by making every possibility inevitable. The popular culture representation of multiverse concepts has also influenced public understanding and scientific discourse. Science fiction films, television shows, and novels routinely explore parallel universes and alternate realities, often in ways that diverge significantly from scientific multiverse theories. These fictional portrayals can both inspire scientific interest and create misconceptions about what multiverse theories actually predict. Hollywood's version of the multiverse typically involves travel between parallel worlds, communication across dimensional barriers, and interactions between alternate versions of the same individuals. While dramatically compelling, these scenarios bear little resemblance to the scientific multiverse, where different regions remain forever causally disconnected and inaccessible to direct observation or interaction. The disconnect between scientific and popular conceptions of the multiverse reflects broader challenges in science communication. The mathematical sophistication of modern physics makes it increasingly difficult to convey accurate scientific concepts to general audiences without significant simplification or distortion. This communication gap can lead to public misunderstanding of what scientists actually study and claim to have discovered. Educational institutions are grappling with how to incorporate multiverse concepts into curricula at various levels. The mathematical prerequisites for understanding eternal inflation or many worlds quantum mechanics are formidable, typically requiring advanced training in quantum field theory, general relativity, and mathematical physics. Yet the philosophical implications of these theories are profound enough that they arguably deserve consideration in broader educational contexts. Some educators have developed approaches that focus on the conceptual and philosophical aspects of multiverse theories while minimizing mathematical complexity. These approaches emphasize critical thinking about evidence, the nature of scientific explanation, and the relationship between theory and observation. Students learn to evaluate competing hypotheses and understand the challenges of testing theories that invoke unobservable phenomena. The international character of multiverse research has also created new models for scientific collaboration that transcend traditional, institutional, and national boundaries. The Planck satellite collaboration involved hundreds of scientists from dozens of countries, pooling expertise and resources to achieve observational capabilities that no single institution could accomplish alone. Similar collaborative models are being applied to gravitational wave detection, particle physics experiments, and theoretical research programs. These collaborative efforts reflect the recognition that addressing fundamental questions about the nature of reality requires resources and expertise that extend far beyond what any individual researcher or institution can provide. The multiverse, if it exists, operates on scales and involves physics that challenge the limits of human understanding and technological capability. Understanding such phenomena requires the collective effort of the global scientific community. The technological demands of multiverse research are also driving advances in computation, instrumentation, and data analysis that find applications far beyond cosmology. The algorithms developed to search for subtle patterns in cosmic microwave background radiation are being adapted for medical imaging, climate modeling, and artificial intelligence applications. The precision instrumentation required for gravitational wave detection has spin-off applications in manufacturing, navigation, and fundamental metrology. Machine learning techniques originally developed for particle physics experiments are now being applied to analyze astronomical datasets for signs of multiverse interactions. These AI systems can identify patterns and correlations that human researchers might miss, potentially revealing subtle signatures of interactions between parallel realities that would otherwise remain hidden in cosmic noise. The quantum computing advances motivated partly by testing many worlds. Interpretations are yielding practical benefits in cryptography, optimization, and simulation of complex quantum systems. Even if these experiments never definitively prove the existence of parallel worlds, they are advancing our understanding of quantum mechanics and its technological applications. Looking toward the future, several emerging technologies and experimental programs offer new possibilities for testing multiverse theories. The next generation of cosmic microwave background experiments will achieve unprecedented sensitivity to polarization patterns that might reveal signatures of quantum entanglement between universes. Ground-based telescopes with adaptive optics systems will map the large-scale structure of the universe with extraordinary precision, potentially detecting subtle anomalies that indicate interactions with parallel realities. Space-based gravitational wave detectors, scheduled for the late 2020s and 2030s, will probe frequency ranges inaccessible from Earth, potentially detecting primordial gravitational waves from the epoch of cosmic inflation. These observations could provide direct evidence for the physical processes that create bubble universes in eternal inflation scenarios. Advanced particle physics experiments at the Large Hadron Collider and future colliders may discover evidence for extra dimensions or supersymmetric particles predicted by string theory. Such discoveries would strengthen the theoretical frameworks that naturally lead to multiverse scenarios, even if they don't directly detect other universes. The development of quantum computers with thousands or millions of quantum bits may enable tests of quantum mechanics that probe the boundaries between different interpretations. While these experiments may never definitively prove the many worlds interpretation, they could reveal quantum phenomena that are most naturally explained by parallel reality processing. Yet even as technology advances and experimental capabilities improve, the fundamental challenge of observing the unobservable remains. The multiverse, if it exists, may be structured in ways that make empirical verification inherently impossible. Different regions of eternal inflation remain causally disconnected by definition. Parallel branches of quantum mechanics cannot communicate with each other without destroying the quantum coherence that supposedly creates them. This observational limitation forces us to confront profound questions about the relationship between physical reality and human knowledge. Can something be real if it can never be observed? How do we distinguish between mathematical consistency and physical existence? What criteria should we use to evaluate theories that transcend the traditional boundaries of empirical science? Some researchers have proposed that these questions reflect an outdated conception of scientific methodology that emerged from studying macroscopic phenomena accessible to direct observation. Modern physics routinely deals with entities and processes that cannot be directly observed, from quantum fields to black hole interiors. The multiverse may simply represent the next step in this progression toward theories that describe reality beyond the reach of immediate experience. Others maintain that abandoning empirical testability would fundamentally alter the nature of science, transforming it from an enterprise grounded in observation into something closer to mathematics or philosophy. They argue that maintaining the connection between theory and experiment is essential for ensuring that scientific knowledge remains relevant to understanding the natural world. The resolution of this debate may ultimately depend on whether multiverse theories prove capable of making successful predictions about observable phenomena, even if the multiverse itself remains unobservable. If eternal inflation correctly predicts the statistical properties of cosmic microwave background fluctuations, if many worlds, quantum mechanics, enable superior quantum computing algorithms, and if string theory landscapes explain the values of fundamental constants, then these theories may earn acceptance through their predictive success, rather than direct verification of their multiverse implications. Alternatively, future discoveries might reveal that our universe is far stranger than current multiverse theories suggest. Perhaps the apparent fine-tuning of physical constants reflects deeper principles we haven't yet discovered. Perhaps quantum mechanics operates according to hidden variable theories that eliminate the need for parallel worlds. Perhaps cosmic inflation was a one-time event that didn't lead to eternal bubble production. The history of physics is filled with theories that seemed compelling at the time, but were eventually superseded by deeper understanding. The luminiferous ether, phlogiston theory, and steady-state cosmology all had sophisticated mathematical formulations and seemed to explain observed phenomena, yet they were ultimately replaced by more accurate descriptions of natural processes. Multiverse theories may face a similar fate, not because they are unobservable, but because they are incomplete or incorrect descriptions of physical reality. Future theoretical developments might reveal that what we interpret as evidence for multiple universes actually reflects more subtle aspects of a single, extraordinarily complex cosmos. The search for understanding continues regardless desire to comprehend our place in the gran of these uncertainties, driven by the fundamental human scheme of existence. Whether the multiverse proves to be a physical reality, a useful mathematical tool, or an interesting historical footnote in the development of physics, the questions it raises about the nature of reality, observation, and scientific knowledge will continue to challenge and inspire researchers for generations to come. As you drift through these final moments before sleep, consider that the very capacity to contemplate infinite realities represents something remarkable about consciousness and cosmos alike. In a universe that may be just one among countless others, the ability to ask questions about existence, to wonder about parallel worlds, and to seek understanding through careful observation and mathematical reasoning becomes a precious gift that connects us to the deepest mysteries of reality itself. The gentle rhythm of your breathing participates in the quantum processes that some theories suggest create parallel worlds with each measurement and interaction. Your thoughts tonight might be branching across multiple realities, exploring different possibilities in the vast space of potential experiences that quantum mechanics seems to permit. Whether those parallel thoughts exist as physical realities or remain mathematical abstractions, they represent the universe's extraordinary capacity for complexity, beauty, and self-reflection through conscious observers like yourself. In contemplating the multiverse, we touch something infinite and profound, a mystery that may forever remain beyond complete understanding, yet continues to inspire our deepest curiosity about the nature of existence and our remarkable place within it. Tonight, as consciousness fades into the quantum realm of dreams, where the normal rules of logic and causality relax, you join the ancient human tradition of wondering about realities beyond immediate experience. The questions that have kept physicists awake for decades now accompany you into sleep, where the boundaries between possible and actual, between one universe and many, become beautifully, mysteriously permeable in the theatre of the dreaming mind. Yet these theoretical frameworks, as elegant as they appear in mathematical formulation, face a more fundamental challenge than mere observational difficulty. The question isn't simply whether we can detect other universes, but whether the concept of detection itself has meaning when applied to realities that exist beyond all possible causal contact with our own. Dr. George Ellis of the University of Cape Town has spent decades wrestling with this conceptual puzzle. A distinguished cosmologist who worked alongside Stephen Hawking on the mathematics of space-time singularities, Ellis argues that multiverse theories blur the crucial distinction between what exists and what is merely mathematically possible. In his view, physics must remain anchored to phenomena that can, in principle, influence observable reality. Ellis points out that the scientific method developed precisely because it provided a reliable way to distinguish between accurate descriptions of nature and appealing but incorrect ideas about how the world works. By requiring that theories make testable predictions, science avoided the endless debates that characterized natural philosophy before the advent of controlled experimentation. But multiverse theories seem to sidestep this empirical constraint entirely. If other universes exist beyond all possible observation, then claims about their properties become unfalsifiable by definition. No conceivable experiment could prove that bubble universes don't exist, that quantum mechanics doesn't branch into parallel worlds, or that the string landscape doesn't encompass infinite variations of physical law. This unfalsifiability troubles many researchers who see it as a departure from the principles that made modern physics so remarkably successful. Karl Popper's philosophy of science emphasized that genuine scientific theories must be capable of being proven wrong through observation. Theories that can accommodate any possible experimental result cease to be scientific hypotheses and become metaphysical doctrines. Yet defenders of multiverse research argue that this criticism reflects an overly narrow conception of scientific methodology. They point out that many accepted features of modern physics involve entities that cannot be directly observed. The interior of black holes lies beyond any possible observation, yet physicists confidently discuss what happens to matter that crosses the event horizon. Quarks cannot be isolated and studied individually, yet their existence is universally accepted based on indirect evidence. The key difference, critics respond, is that these unobservable phenomena still have observable consequences. Black holes affect the motion of nearby stars and gas, allowing their properties to be inferred through gravitational effects. Quarks combine to form protons and neutrons, whose behavior can be studied in detail through particle accelerator experiments. Other universes, by contrast, seem to be defined precisely by their lack of observable consequences. If bubble universes were close enough to influence our cosmic evolution, they would cease to be separate universes and become part of our extended cosmos. If parallel quantum worlds could communicate with our reality, they would collapse back into a single quantum system rather than remaining separate branches. This isolation appears to be fundamental rather than merely technological. No conceivable advance in instrumentation could allow us to peer into other bubble universes or communicate with parallel quantum worlds. The theories themselves predict that such contact is impossible, not just practically difficult, but logically contradictory. Dr. Jim Baggott, a science writer and former research scientist, has articulated this concern in particularly stark terms. He argues that multiverse theories represent a crisis in physics, where mathematical elegance has become divorced from empirical reality. In his view, the field is drifting toward what he calls fairy tale physics, where beautiful mathematical structures are mistaken for descriptions of the natural world. Baggott's critique extends beyond multiverse theories to encompass what he sees as a broader trend in theoretical physics toward increasingly abstract and untestable speculation. String theory, supersymmetry, and extra dimensions all suffer from similar problems, he argues, creating elaborate mathematical edifices with little connection to observable phenomena. The concern isn't merely academic. Physics departments around the world are training graduate students to work on multiverse theories, quantum gravity, and string cosmology. Talented young researchers are dedicating their careers to problems that may have no solution, or worse, no meaningful connection to physical reality. Meanwhile, other areas of physics that could yield practical benefits receive less attention and resources. Climate physics, condensed matter research, and plasma physics all offer opportunities to address pressing human needs while advancing fundamental understanding. The opportunity cost of multiverse research may be measured not just in abstract knowledge, but in concrete applications that could improve human welfare. Yet this utilitarian argument faces its own challenges. The history of physics is filled with apparently abstract investigations that later yielded unexpected practical applications. Einstein's general relativity seemed like pure mathematical speculation when first proposed. Yet it now enables the GPS satellites that guide modern navigation. Quantum mechanics emerged from attempts to understand atomic spectra, but it eventually revolutionized electronics and computing. Michael Faraday, when asked about the practical value of electricity, reportedly replied that he didn't know, but was confident the government would eventually find a way to tax it. Similarly, multiverse research might seem impractical today, but could eventually lead to technological breakthroughs we cannot currently imagine. The debate over multiverse theories also reflects deeper tensions about the role of beauty and elegance in scientific reasoning. Many of the most successful theories in physics exhibit remarkable mathematical elegance, from the symmetries of Maxwell's equations to the geometric perfection of Einstein's field equations. This pattern has led some researchers to treat mathematical beauty as a reliable guide to physical truth. Dr. Sabine Hossenfelder of the Frankfurt Institute for Advanced Studies has challenged this assumption directly. Her research into the foundations of physics suggests that the pursuit of mathematical elegance may actually mislead scientists, causing them to prefer theories that are aesthetically appealing rather than empirically accurate. Hossenfelder points out that nature has no obligation to conform to human aesthetic preferences. The most accurate description of reality might be mathematically ugly, involving arbitrary parameters and asymmetric structures that offend our sense of mathematical beauty. By privileging elegant theories over empirically grounded ones, physics may be heading down a path that leads away from understanding the natural world. The multiverse debate has also been influenced by broader cultural and philosophical currents that extend well beyond physics. The concept of parallel worlds resonates with postmodern ideas about multiple perspectives and the socially constructed nature of reality. Some critics worry that multiverse theories reflect these cultural influences rather than genuine insights into the structure of the cosmos. Conversely, supporters argue that the resistance to multiverse theories stems from deeply ingrained human biases about uniqueness and significance. We are psychologically predisposed to believe that our universe is special, that our existence is cosmically meaningful, and that the physical laws we observe represent the only possible way reality could be structured. These biases, they contend, prevent us from accepting the logical implications of our best theories about quantum mechanics and cosmic evolution. Just as Copernicus challenged the assumption that Earth occupied a privileged position in the cosmos, multiverse theories challenge our assumption that our universe represents the entirety of physical reality. Dr. Max Tegmark has pushed this reasoning to its logical extreme in his mathematical universe hypothesis. If we accept that mathematical structures describe physical reality, he argues, then we must also accept that all mathematical structures correspond to some form of physical existence. The multiverse isn't just a collection of universes with different physical constants, but encompasses every logically consistent mathematical framework. In Tegmark's vision, we inhabit what he calls the level 4 multiverse, where abstract mathematical objects like numbers, geometric shapes, and algebraic equations are as real as stars and planets. Consciousness doesn't emerge from material processes, but represents self-aware mathematical structures contemplating their own logical consistency. This mathematical universe hypothesis pushes against the boundaries of what most physicists are willing to accept. Even researchers sympathetic to multiverse theories often find Tegmark's vision too radical, too divorced from anything resembling empirical science. Yet his arguments follow logically from premises that many physicists do accept, highlighting the conceptual challenges that arise when we try to understand the relationship between mathematics and physical reality. The question of consciousness itself becomes particularly puzzling in multiverse scenarios. If every possible arrangement of matter and energy exists somewhere in the multiverse, then conscious observers, like ourselves, exist in countless variations across different realities. Some versions might differ only in trivial details, while others might have completely different sensory experiences or cognitive capabilities. This multiplicity of conscious observers raises profound questions about personal identity and the nature of subjective experience. Are you the same person as your identical counterparts in other universes? If your consciousness branches with every quantum measurement, which branch represents the real you? Do all possible versions of yourself have equal claim to being genuine? Or is there something special about the particular branch you happen to experience? These questions extend beyond philosophy into practical considerations about decision-making and moral responsibility. If every possible choice you might make is realized somewhere in the multiverse, do your individual decisions matter? Some philosophers argue that moral responsibility becomes meaningless in a multiverse where every possible action occurs regardless of your personal choices. Others contend that this reasoning commits a category error by confusing what happens across the entire multiverse with what matters from your particular perspective as a conscious observer. Even if all possible versions of your life play out somewhere in the multiverse, you can only experience one branch directly, making your choices significant from your own subjective viewpoint. The many worlds interpretation of quantum mechanics faces similar conceptual challenges. If consciousness splits with every quantum measurement, creating parallel versions of yourself that experience different outcomes, why do you seem to experience only one definite reality rather than a superposition of all possibilities? Some researchers have proposed that consciousness itself might play a role in selecting which branch of quantum reality becomes experienced. This idea connects to older interpretations of quantum mechanics that emphasize the role of observation in determining physical outcomes. However, it also raises difficult questions about what constitutes consciousness and how mental processes could influence quantum evolution. Dr. Roger Penrose and Dr. Stuart Hameroff have developed one of the most detailed theories connecting consciousness to quantum mechanics. They propose that microtubules within brain cells might maintain quantum coherence at body temperature, allowing consciousness to emerge from quantum computational processes that span multiple parallel realities. While their orchestrated objective reduction theory remains controversial among neuroscientists, it illustrates how seriously some researchers take the connection between consciousness and quantum multiverse scenarios. If consciousness does emerge from quantum processes, then the nature of subjective experience might be intimately connected to the structure of parallel realities. The search for experimental evidence continues despite these conceptual challenges. The most promising near-term possibilities involve testing the theoretical frameworks that predict multiverse scenarios rather than directly detecting other universes. If eternal inflation theory, many worlds quantum mechanics, or string theory can be validated through other means, their multiverse implications gain credibility even without direct confirmation. The Large Hadron Collider continues to probe the fundamental structure of matter at unprecedented energies, searching for evidence of extra dimensions, supersymmetric particles, or other exotic phenomena predicted by theories that naturally lead to multiverse scenarios. While no definitive discoveries have emerged yet, the ongoing experimental program continues to constrain theoretical possibilities and could potentially reveal physics that supports multiverse predictions. Future particle accelerators with even higher energies might probe deeper into the fundamental structure of reality, potentially accessing energy scales where string theory effects become apparent or where the extra dimensions required by multiverse scenarios begin to manifest. These experiments represent some of humanity's most ambitious attempts to understand the deepest levels of physical reality. Cosmological observations also continue to advance, with increasingly sensitive measurements of the cosmic microwave background, gravitational waves, and large-scale structure providing new windows into the early universe. The recently launched James Webb Space Telescope is already revealing unprecedented details about the formation of the first galaxies, potentially preserving information about the cosmic inflation process that might have created our bubble universe. The European Space Agency's planned LISA gravitational wave detector will operate in space, providing access to gravitational wave frequencies that cannot be observed from Earth. These space-based observations might detect primordial gravitational waves from cosmic inflation, providing direct evidence for the physical processes that multiverse theories invoke to explain our cosmic origins. Advanced ground-based gravitational wave detectors, like the proposed Einstein telescope, could achieve sensitivities that allow detection of gravitational waves from phase transitions in the early universe, cosmic string networks, or other exotic phenomena associated with multiverse scenarios. These observations would probe physics at energy scales and time periods that cannot be accessed through any other means. Quantum technology continues to advance as well, with increasingly sophisticated quantum computers and quantum communication systems providing new ways to test the foundations of quantum mechanics. While these experiments may never definitively prove the many worlds interpretation, they continue to reveal the strange and counterintuitive nature of quantum reality. Some researchers have proposed that advanced quantum computers might eventually be capable of detecting interference effects between different branches of quantum reality, providing indirect evidence for parallel worlds. While such experiments remain speculative, they illustrate how technological progress continues to open new possibilities for testing fundamental theories about the nature of reality. The international collaboration required for these advanced experiments continues to strengthen, with researchers from dozens of countries contributing to projects like the Large Hadron Collider, LIGO gravitational wave detection, and cosmic microwave background analysis. This global cooperation reflects the recognition that understanding fundamental questions about reality requires resources and expertise that transcend national boundaries. educational institutions are also grappling with how to incorporate multiverse concepts into physics curricula. The mathematical sophistication required to understand eternal inflation, many worlds, quantum mechanics, and string theory landscapes present significant pedagogical challenges. Yet the philosophical implications of these theories are profound enough that they arguably deserve consideration in broader educational contexts. Some educators have developed approaches that emphasize the scientific methodology used to evaluate multiverse theories rather than the detailed mathematics of the theories themselves. Students learn to think critically about evidence, testability, and the relationship between mathematical consistency and physical reality. These skills are valuable regardless of whether multiverse theories ultimately prove correct. The popular culture representation of multiverse concepts continues to evolve as well, with science fiction films and television shows exploring increasingly sophisticated versions of parallel reality scenarios. While these fictional portrayals often diverge significantly from scientific multiverse theories, they help maintain public interest in fundamental questions about the nature of reality and our place in the cosmos. Science museums and planetariums around the world have developed exhibits that attempt to convey the wonder and complexity of multiverse theories to general audiences. These educational efforts face the challenge of making abstract mathematical concepts accessible while maintaining scientific accuracy and avoiding oversimplification. The economic implications of multiverse research extend beyond direct scientific applications. The technological advances required for testing multiverse theories drive innovation in areas like precision instrumentation, data analysis, and high-performance computing that find applications throughout the economy. The international collaborations fostered by multiverse research also strengthen scientific and technological ties between nations. Some private organizations have begun investing in multiverse-related research, recognizing its potential for advancing fundamental understanding and driving technological innovation. The Templeton Foundation has funded numerous projects exploring the philosophical implications of multiverse theories, while technology companies have supported quantum computing research that could eventually test many worlds' interpretations. Looking toward the future, several emerging technologies and experimental programs offer new possibilities for testing multiverse theories. Advances in quantum computing may enable simulations of cosmological scenarios that are too complex for classical computers, potentially revealing new insights into eternal inflation and bubble universe formation. Machine learning and artificial intelligence techniques are being applied to analyze vast astronomical datasets for subtle patterns that might indicate multiverse interactions. These AI systems can process enormous amounts of data with superhuman speed and accuracy, potentially discovering signatures that human researchers would miss. The development of space-based telescopes with unprecedented sensitivity and resolution will provide new windows into the early universe and the large-scale structure of the cosmos. These observations might reveal anomalies or patterns that support multiverse predictions, though they could equally well reveal phenomena that challenge current theoretical frameworks entirely. Advanced materials research might eventually enable the construction of gravitational wave detectors with sensitivity far beyond current capabilities, potentially detecting signals from the earliest moments of cosmic history when multiverse-generating processes might have been active. Similarly, advances in quantum sensor technology could provide new ways to probe the fundamental structure of space and time. Yet even as technology advances and experimental capabilities improve, the fundamental conceptual challenges surrounding multiverse theories remain. The question of what constitutes scientific knowledge when dealing with potentially unobservable phenomena continues to generate debate among physicists, philosophers, and educators. Some researchers are exploring alternative approaches to these conceptual challenges, developing new frameworks for understanding the relationship between mathematical models and physical reality. These approaches might eventually provide ways to evaluate multiverse theories that don't depend on direct observational confirmation of other universes. Others are investigating whether multiverse theories might make subtle but testable predictions about observable phenomena that haven't yet been recognized. Perhaps the statistical properties of cosmic structure, the behavior of quantum systems, or the values of fundamental constants contain hidden signatures of multiverse physics that future analysis might reveal. The possibility also remains that multiverse theories are simply incorrect, interesting mathematical exercises that don't correspond to physical reality. Future theoretical developments might reveal more elegant explanations for apparent fine-tuning, quantum measurement, and cosmic inflation that don't require invoking unobservable parallel realities. Alternatively, entirely new physics might emerge that transcends current multiverse scenarios while preserving their most successful predictions. The history of science is filled with theoretical frameworks that seemed comprehensive at the time, but were eventually superseded by deeper understanding that incorporated their insights while revealing new layers of complexity. The search for understanding continues regardless of these uncertainties, driven by the fundamental human desire to comprehend our place in the grand scheme of existence. Whether multiverse theories prove to represent genuine insights into the nature of reality or interesting detours in the history of physics, they have already contributed to expanding our conception of what might be possible. In pushing the boundaries of scientific thinking, multiverse research has forced physicists to confront fundamental questions about observation, explanation, and the limits of human knowledge. These conceptual challenges have value independent of whether other universes actually exist, strengthening our understanding of the scientific method and its proper application to phenomena that stretch the limits of empirical investigation. The mathematical techniques developed for multiverse research have found applications throughout theoretical physics, from condensed matter systems to black hole physics to quantum information theory. The international collaborations fostered by multiverse research have strengthened scientific cooperation and created new models for addressing complex interdisciplinary problems. Perhaps most importantly, multiverse theories have inspired a new generation of physicists to think boldly about the nature of reality and to push against conventional boundaries in their search for understanding. This willingness to explore radical possibilities while maintaining rigorous standards of evidence represents the best tradition of scientific inquiry. As you settle into the quiet moments before sleep, consider that the very capacity to contemplate infinite realities represents something remarkable about consciousness and its relationship to the cosmos. Whether those realities exist as physical entities or mathematical abstractions, the ability to conceive them reflects the extraordinary power of human thought to transcend the immediate boundaries of experience. The gentle rhythm of your breathing connects you to quantum processes that some theories suggest create branching realities with each interaction. Your thoughts tonight might explore possibilities that span multiple universes, touching questions that have puzzled humanity since we first looked up at the stars and wondered what lies beyond the visible horizon. In contemplating the multiverse, we participate in an ancient human tradition of seeking to understand our place in existence. The questions that drive multiverse research: why does the universe have the properties it does? Are we alone in the cosmos? What is the nature of reality itself? Echo the deepest concerns of philosophy and religion while requiring the precision and rigor of mathematical physics. Whether the multiverse exists as described by current theories, whether it takes forms we haven't yet imagined, or whether reality proves to be something entirely different, the search for understanding enriches our appreciation of existence and our role as conscious observers in a cosmos that may be far stranger and more wonderful than we can currently comprehend. Tonight, as consciousness fades into the realm of dreams where the boundaries between possible and actual become beautifully permeable, you join the ongoing human conversation with mystery itself, the questions about parallel realities and infinite universes that have challenged physicists for decades now accompany you into sleep, where the normal constraints of logic and causality relax, allowing the mind to explore possibilities that may forever remain beyond the reach of scientific observation, but continue to inspire our deepest wonder about the nature of existence and our extraordinary place within it. The gentle darkness that surrounds you tonight isn't empty, but full of possibilities that stretch beyond anything our ancestors could have imagined. Each photon of starlight that reaches your eyes has travelled across vast distances, carrying information from cosmic epochs when the universe was young and strange. Yet even this ancient light represents only the tiniest fraction of what might actually exist beyond the boundaries of our perception. The observable universe, that sphere of reality we can actually detect and study, extends roughly 46 billion light-years in every direction from Earth. This might seem impossibly vast, containing as it does over 2 trillion galaxies, each harbouring billions of stars. But here's where the story becomes truly extraordinary. Beyond this cosmic horizon lies something that challenges our most fundamental assumptions about the nature of existence itself. Think of it this way: when you stand on a beach and look out toward the ocean, your view is limited by the Earth's curvature. You know there's more ocean beyond what you can see, but the horizon creates a natural boundary to your observation. Our cosmic situation is remarkably similar, except the horizon isn't created by planetary geometry, but by the fundamental speed of light and the finite age of our universe. This realization has led cosmologists to contemplate one of the most profound questions in all of science. If we can only observe a finite region of space, what lies beyond? The answer, according to some of our most brilliant theoretical physicists, might be far stranger than even the most imaginative science fiction has dared to suggest. Dr. Alan Guth was working late in his office at the Stanford Linear Accelerator Center in December of 1979 when he scribbled a note in his laboratory notebook that would forever change how we think about cosmic origins. The word spectacular appears in capital letters, circled emphatically, next to calculations that would eventually lead to one of the most revolutionary ideas in modern cosmology. Guth had been wrestling with some troubling problems in Big Bang theory. Why was the universe so remarkably flat when basic physics suggested it should be curved? Why did regions of space that had never been in causal contact show nearly identical temperatures? The solutions emerging from his calculations seemed almost too elegant to be true. His proposal was called cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, space itself underwent a period of exponential expansion. During an interval shorter than the time it takes light to cross a proton, a region smaller than a subatomic particle expanded to dimensions larger than a grapefruit. This stupendous stretching would smooth out any initial irregularities and create the flat, uniform universe we observe today. But inflation theory contained within it the seeds of something even more remarkable. The same quantum fluctuations that drive the inflationary process don't end everywhere simultaneously. While inflation stops in some regions, allowing matter and energy to condense into galaxies and stars, it continues elsewhere, creating new domains that undergo their own inflationary epochs. Dr. Andrei Linde, working independently at the Lebedev Physical Institute in Moscow, developed this insight into what became known as eternal inflation. In his chaotic inflation model, the universe becomes a self-reproducing system where new regions are constantly branching off from inflating domains, each eventually undergoing its own Big Bang-like transition when inflation ends locally. Picture a vast ocean where bubbles are constantly forming and expanding. Each bubble represents what we might call a universe, complete with its own space, time, matter, and energy. Our observable cosmos would be just a tiny region within one such bubble, while countless other bubbles expand and evolve according to their own physical laws throughout the eternal sea of inflating space. Linda describes this scenario with almost poetic wonder. Instead of a universe with a single set of physical laws, eternal chaotic inflation predicts a self-reproducing, eternally existing multiverse where every possibility that quantum mechanics allows eventually becomes realized. Somewhere in this vast ensemble of bubble universes, he suggests, another version of you is contemplating these very same ideas, perhaps reaching different conclusions about their implications. The mathematics underlying eternal inflation are both beautiful and unsettling in their scope. If the theory is correct, then everything that can happen will happen. Not just once, but infinitely many times across the boundless collection of bubble universes. Every possible arrangement of atoms, every potential outcome of quantum events, every conceivable variation of physical constants gets actualized somewhere in the multiverse. This connects to one of the most perplexing puzzles in all of physics, what researchers call the fine-tuning problem. The fundamental parameters of nature, from the strength of gravity to the mass of the electron, appear to be calibrated with extraordinary precision to permit the formation of stars, planets, and ultimately life itself. Consider the cosmological constant, the energy density of empty space that drives the accelerating expansion of our universe. Quantum field theory suggests this quantity should be enormous, roughly 10 to the 120th power times larger than what we actually observe. This represents perhaps the worst theoretical prediction in the history of science. Yet somehow, our universe ended up with a cosmological constant so small it allows galaxies to form and persist. Change this parameter by even a tiny amount, and the consequences would be catastrophic. A slightly larger value would cause space to expand so rapidly that matter could never clump together into cosmic structures. A negative value of similar magnitude would cause the entire universe to collapse before stars could ignite and burn. The same delicate balance appears throughout the fundamental constants. Increase the strength of the strong nuclear force by just 5%, and hydrogen would be unstable, preventing the formation of water and organic chemistry. Decrease it by the same amount, and nuclear fusion in stellar cores would shut down, leaving the universe cold and dark. The mass ratios of elementary particles, the relative strengths of the four fundamental forces, even the number of spatial dimensions all seem precisely tuned to permit complexity and life. In a single universe scenario, this fine-tuning appears to require either extraordinary coincidence or intelligent design. The probability that all these parameters would randomly fall within life-permitting ranges is so vanishingly small that it challenges credibility. Yet eternal inflation provides an elegant alternative explanation through what physicists call the Anthropic principle. If different regions of the multiverse have different values of these fundamental constants, then fine-tuning becomes a selection effect rather than a cosmic mystery. We observe life-permitting parameters not because they were specially chosen, but because we could only have evolved in a region where such parameters allow for our existence. The vast majority of bubble universes might be sterile and lifeless, but observers can only emerge in the tiny fraction where conditions happen to support complexity. Dr. Steven Weinberg demonstrated the power of this anthropic reasoning in the 1980s when he used multiverse arguments to predict the value of the cosmological constant years before it was measured. His calculation suggested the constant should be small but positive, just barely consistent with galaxy formation. When observations of distant supernovae confirmed cosmic acceleration in the 1990s, Weinberg's anthropic prediction proved remarkably accurate. This success has encouraged researchers to apply similar reasoning to other fine-tuning problems, though not without controversy. critics argue that anthropic explanations are inherently post hoc, designed to explain existing observations rather than make genuine predictions about new phenomena. They worry that accepting such reasoning could lead physics away from its traditional goal of finding unique, testable theories toward a more speculative enterprise that explains everything while predicting nothing specific. Meanwhile, quantum mechanics offers its own pathway to multiple realities through an interpretation that eliminates one of the theory's most puzzling features. Since the early days of quantum physics, researchers have grappled with the measurement problem. Why do particles exist in multiple states simultaneously until observed, at which point they mysteriously collapse into single, definite properties? Hugh Everett III proposed a radical solution in his 1957 doctoral thesis at Princeton University. Rather than accepting that quantum measurements cause wave functions to collapse, Everett suggested that all possible outcomes actually occur simultaneously in parallel branches of reality. This many-worlds interpretation eliminates the arbitrary boundary between quantum and classical physics by treating everything as fundamentally quantum mechanical. In Everett's vision, every quantum interaction throughout the universe constantly splits reality into multiple branches. Each possible outcome of every quantum measurement gets realized in a different branch, creating an ever-proliferating tree of parallel worlds. These worlds are completely real, but forever isolated from one another, making direct communication or travel between them impossible. Dr. David Deutsch of Oxford University has become one of the most eloquent advocates for the many worlds interpretation, connecting it to quantum computation and information theory. He argues that quantum computers derive their extraordinary power from performing calculations across multiple parallel worlds simultaneously, harnessing the computational resources of the multiverse to solve problems that would be intractable for classical systems. When a quantum computer processes information, Deutsch suggests, it isn't just manipulating quantum bits in our reality, but coordinating calculations across countless parallel versions of itself. The final answer emerges from a kind of quantum democratic process where different branches explore different solution paths before converging on the result that appears in our particular world. The scale of branching in the many worlds interpretation is truly staggering. Dr. Max Tegmark of MIT calculates that the number of parallel worlds grows exponentially with each passing moment, as every quantum transition throughout the observable universe creates new branches. Every atomic decay, every photon absorption, every neural firing in your brain right now potentially splits reality into multiple versions where slightly different outcomes occur. This quantum multiverse operates on completely different principles than the bubble universes of eternal inflation. While inflating domains are separated by physical space and might evolve under different laws of physics, the parallel worlds of quantum mechanics are superimposed in the same space, but isolated by the fundamental structure of quantum reality itself. They represent different branches of the universal wave function, each as complete and real as our own experienced reality. String theory contributes yet another vision of the multiverse through what researchers call the landscape of possible universes. This ambitious theoretical framework attempts to unify all fundamental forces by describing particles as tiny vibrating strings rather than point-like objects. But string theory requires additional spatial dimensions beyond the three we observe, and these extra dimensions must be compactified in ways that remain hidden at everyday scales. Dr. Leonard Susskind of Stanford University has explored the implications of this dimensional compactification in extraordinary detail. The mathematical complexity of string theory allows for an astronomical number of ways to curl up the extra dimensions, each leading to different physical laws and constants in the resulting four-dimensional universe. Current estimates suggest the number of possible configurations could exceed 10 to the 500,000th power. When combined with eternal inflation, The string landscape suggests that different regions of the multiverse settle into different string theory configurations, creating bubble universes with dramatically different physical properties. Some might have stronger or weaker forces, different numbers of particle types, or even different dimensional structures entirely. This provides another potential explanation for the apparent fine-tuning of our universe, with all possible values of physical constants being realized somewhere across the vast landscape of possibilities. Yet despite decades of theoretical development and increasingly sophisticated mathematical frameworks, the multiverse remains one of the most contentious ideas in modern physics. The fundamental challenge is observational. By definition, other universes exist beyond our cosmic horizon, or in parallel quantum branches we can never directly access. This apparent untestability has led some critics to argue that multiverse theories venture beyond legitimate science into metaphysical speculation. Dr. Paul Steinhardt, one of the original architects of inflation theory, has become one of the most vocal critics of eternal inflation and its multiverse implications. He argues that the theory has become unfalsifiable and therefore unscientific, capable of accommodating any possible observation by invoking appropriate regions of the multiverse. The debate touches on fundamental questions about the nature of scientific knowledge itself. Traditional approaches to science emphasize testable predictions that can be verified or falsified through observation and experiment. But multiverse theories appear to violate this principle by making claims about entities that may be fundamentally unobservable. Some physicists have responded by developing new criteria for evaluating theories that cannot be directly tested. They focus on explanatory power, mathematical consistency, and the ability to make predictions about observable phenomena, even when the theory invokes unobservable entities. Others remain deeply skeptical, arguing that without empirical contact, these ideas cease to be physics and become something closer to philosophy or mathematics. The search for evidence has led scientists to examine subtle patterns in the cosmic microwave background radiation, that ancient afterglow of the Big Bang that fills all of space. Researchers have looked for signatures that might indicate collisions with other bubble universes, unusual correlations that might suggest quantum entanglement between different realities, or statistical anomalies that deviate from single universe predictions. Dr. Stephen Feeney and his colleagues at University College London made headlines when they claimed to find circular patterns in this primordial radiation that could represent scars from encounters with neighbouring universes. The analysis was extraordinarily complex, requiring sophisticated algorithms to separate potential multiverse signatures from instrumental noise and astrophysical contamination. While initial results seemed promising, more detailed analysis using data from the European Space Agency's Planck satellite failed to confirm the claimed detections. The patterns that had appeared significant dissolved into statistical noise when examined with greater precision, illustrating the extraordinary difficulty of detecting phenomena that exist at the very limits of observational capability. Similar challenges have confronted other attempts to find multiverse evidence. The cosmic microwave background, cold spot, an unusually large and cold region in the southern sky, has been proposed as a possible signature of interaction with another universe. Yet conventional explanations involving cosmic voids and gravitational effects remain favoured by most researchers. The stakes in this debate couldn't be higher. If multiverse theories are correct, they would fundamentally transform our understanding of reality, suggesting that our observable universe represents just one thread in an infinite tapestry of existence. Every question about why the universe has the properties it does would need to be reframed in terms of observer selection effects across an ensemble of realities. But the implications extend beyond abstract philosophy into practical questions about how science should proceed. If we accept that some aspects of reality may be forever beyond direct observation, how do we maintain scientific rigor? How do we distinguish between legitimate, theoretical speculation and untestable metaphysics? The multiverse remains one of science's most beautiful and bewildering frontiers, where rigorous mathematics meets the deepest questions about existence itself. Whether these parallel realities emerge from eternal inflation, quantum branching, or the vast landscape of string theory, they challenge us to expand our conception of what might be possible while maintaining the careful skepticism that defines genuine scientific inquiry. Tonight, as you drift towards sleep, remember that you are part of humanity's grandest adventure, the quest to understand our place in a cosmos that may be far stranger and more magnificent than we ever dared imagine. Sweet dreams, fellow traveller, in the infinite mystery we call reality.